Okay, so I'll let the team from Flow 3D Weld introduce themselves.
Thanks, Dave, and appreciate your organization hosting our webinar. I don't know if you introduced AILU, but we are members since I think late last year, and we are here in the USA. We developed the software Flow 3D Weld, which I'll be talking about today. I am a senior CFD engineer, and I work mostly in welding and additive application modeling.
Hello, everyone. My name is Marcin Serdeczny. I work as a support engineer. So I mostly support our users within laser welding and additive manufacturing sector. I have personally done a PhD in additive manufacturing and modeling. Well, I'm looking forward to the webinar and answering your questions.
Okay, so without further ado, I'm just going to share the screen and give Alice control of the slides. And Alice, you have control.
Thanks, Dave. Dave, I think there's like a little blue thing on the left-hand side. I don't know if that's from your side or if that's from PowerPoint.
Oh, this little blue circle.
Yeah.
Yeah, I don't think, sorry, I'm fighting for control.
It's not going away.
No, it's not going away, sorry. It's
because you have control. Okay. It's
okay, you
okay.
take control?
Yeah, I think I have it. Okay. Actually, let's get this video to start again. There we go. Okay, yes, thanks for joining today, everybody, and thanks again for hosting us. We're going to talk about Meltpool simulations for welding process optimization. So you know what you're looking at on the screen here. This is a pulsed laser welding simulation. That first render view was using a ray tracing, so you get like the light reflections from the actual material. And then the second view is a thermal profile. Okay, so on the agenda, we're going to divide this presentation into 3 sections. We're going to start off by talking about welding defects kind of generally and the impact that they have on the industry. Then we're going to go into defect identification and mitigation and how we approach this from a simulation standpoint. And then we will talk about more so parameter development and how you can use simulation to guide and optimize your weld schedules. So from a business standpoint, there's kind of high consequence for welding defects. And we see this a lot in some product recalls, kind of from the consumer standpoint. So aside from the high cost on the business being, a lot of setback on the order of maybe millions of dollars, sometimes months, years, timelines to get a product out to market. We even sometimes see products pulled from the market entirely, like we did with the Note 7, where among a few different issues, there was notably a laser welding defect that caused the electrodes in the battery to touch, and there were some explosions, there was fires, there was injuries. So high consequence there. We see on the vehicle side of things, of course, vehicles are tens of thousands of dollars each, and pulling back hundreds of thousands of vehicles because of welding defects, sometimes breaking down on the road, causing injury to drivers, causing traffic issues. So there's a lot of, beyond just kind of the business standpoint, there's a lot of things that we need to consider with the Medtronic heart pumps. There's a welding defect in those just last year, and they were recalled. Of course, these are implanted into people's bodies. There was, I think, a few deaths. So there's, very high consequence. We definitely want to look at how we can mitigate welding defects from the source before they get to the consumer. So in terms of what we're kind of trying to mitigate in terms of like a risk assessment here is we want to meet certain quality standards. So eliminating the obvious defects, porosity, cracking, but also achieving more tolerance-based, that's kind of just going on its own, aspects of the process. So you want to have proper fusion, you don't want to overheat and damage sensitive components, especially when you're dealing with like electronics and battery manufacturing. But you also want to be able to produce consistent quality beyond the prototype. So in real life, on the real production floor, there's process variations, there's variations in geometry. And so designing weld schedules to not only produce the desired result in one case, but produce the desired result in all cases that you can design for is a key aspect of delivering quality in your product. So designing those weld schedules to account for the variation, but also being able to catch defects as early as possible before the products go out. So in terms of the kind of physics at play here, we're looking at very complex thermal and fluid flow phenomenon. When you're melting a metal, it's undergoing heat transfer, convection, radiation. There's phase changes happening from solid to liquid to vapor. So there's a lot at play here that is going into the stability of the process. And then this stability is very sensitive to the process parameters. So what speed you're going at, what heat flux you have, the power delivery. There's a lot of different factors that play into the process stability. And on top of this, there's a lot of applications for laser welding where they're trying to join dissimilar materials. So that creates a further complexity where you have the complex fluid thermal phenomenon of 2 independent or maybe 3 independently defined alloys. So there's limits in terms of the experimental capabilities to really monitor the influence of the process parameters in the situation. So we can see this video on the top right. This is from a Cavatar camera, very, very nice high resolution capturing of this laser welding process. But despite, the fact that we can very clearly see the fluid flow, the spatter, you can't get an indication of what the local temperatures are. You don't know what the thermal gradients are. You don't know where the solidification front is. You don't know what the mass flux due to vaporization, how much material is getting evaporated. So these types of things is where we look to simulation to really understand more holistically what the implications of process parameters are on our process. So looking into any sources of defects, the commonality amongst pretty much all of these kind of defects that we see in the joint fusion itself is related to fluid flow, heat transfer, and solidification. That's at the heart of what we see on the screen here, where, for instance, in Meltpool, in Keyhole induced porosity, like we have on the bottom left here, this is due to unstable keyhole dynamics, unstable Meltpool dynamics, and then gas being trapped inside of the material. So all fluid flow, heat transfer, solidification related, excessive heating over melting, like we see here on the bottom right, leading to spatter, like we saw in the last video. And then insufficient heating, lack of fusion, balling, like we see here on the top right. This is all kind of related back to those 3 kind of fundamentals that we can use the simulation to further understand. So naturally, we are a computational fluid dynamics company, so we're in the business of controlling fluid flow. And this stability in the process is going to depend on kind of some basic fundamental aspects. So the temperature gradients, the convection, so that's the fluid flow aspect, and then the vaporization, which leads to recoil forces, and that's going to be the kind of plume side of things. So there's different aspects of the process that have different fluid flow kind of conditions, but it's something that we account for from the fluid dynamics perspective. So we're looking deeply into this transient process dynamics to understand this process in a much more holistic way. And we really want to pull this back to what is the sensitivity of the process to the given process parameters, and how is that triggering defects, and what does that evolution look like? How can we then control the process to avoid those costly defects? So just as an example of a way to kind of think about this problem. So we have a video here. This is provided by a user a few years back, where they were looking at oscillation welding as a way to create process stability. And through the simulation, they found that with this oscillation technique, they were going between a keyhole and a conduction regime. So they were never really getting into that sustained keyhole regime that was leading to the instabilities. They were able to leverage the kind of oscillations to create a really nice joint there. So Flow3D Weld is the software that we develop. It is a computational fluid dynamic software at its core, but it is designed specifically to model fluid flow and solidification in welding processes. So we can look at things like temperature evolution, predict bead cross sections, predict the melted volume, the surface roughness, the relative porosity, both micro and macro porosity. And generally it's used by people working in R&D, process engineers who are trying to develop weld schedules for maybe new materials, new applications, or trying to fix critical defects that they're seeing in their existing process. So what we deliver here is an accurate prediction of the melt pool dynamics, the solidification. That's at the core of all of these process dynamics and your result. The thermal gradients, the heat affected zones, this is going to have a direct implication on your mechanical properties. And then, of course, the defects like porosity, lack of fusion, spatter. So looking into defect identification and mitigation, we're actually going to talk about this case here in the image, which came from General Motors, where they were looking into mitigating that porosity in these laser welded aluminum joints, and specifically how they could use the process parameters to affect the keyhole dynamics that were directly related to the porosity. So this configuration was a lap joint of this aluminum alloy here that had a high magnesium content, which was leading to a lot of porosity because of the low vaporization point of magnesium. So they used simulations to replicate the experiments, in this case, which were done with the 6 kilowatt IPG laser. So just to understand this process on a fundamental level, and that's kind of how we build our knowledge to the point that we can actually make intelligent and evidence-based decisions on the weld schedule. So understanding the porosity formation at its core and the transient and how does it actually happen is really key here. So that's what they did in this study, where they looked at the instabilities that were leading to the collapse initially. So we can see in this process, to start off, you have a keyhole that starts to form. You have this recoil pressure that happens where you have mass flux due to vaporization. And that creates this downward force that really drives the keyhole. And then as that keyhole continues to penetrate into the material, you have this sort of recoil pressure that becomes a bit more spaced out along the free surface. And then it kind of pushes back towards the molten flow, where you have this propensity of this kind of recirculation zone back here. And then this becomes unstable at some point. If you have too much depth to width ratio, you get this really elongated keyhole, and you get these sort of irregular shaped sidewalls, and they tend to want to collapse. And when they collapse, you get this bridging. This is due to surface tension. They kind of want to like join together like a droplet sitting next to another droplet, and then you get this bubble formation. So once that bubble forms, there's buoyant effects within it. So it's a lighter, it has a lower density, of course. It's a gas but inside of a liquid. So it wants to migrate to the surface of the material. And it can do that in some cases. It has enough time, but in other cases, it does not. And so once that, because these processes tend to have very high solidification rates, very high cooling rates, this solidification front will come in and it'll trap those bubbles pretty much instantaneously. And in some cases, like I said, they get released. But what you end up with is a lot of porosity. So what they looked at in this case specifically was how can we use the welding speed to mitigate that porosity, and what is the welding speed due to the keyhole stability that's leading to that porosity formation. So what they found through these simulations was that with a higher speed, so that's on the right-hand side here, you get this larger keyhole opening. That's because everything's kind of moving faster. This front keyhole wall is moving away from this rear keyhole wall, and then you get this larger opening, and that leads to the laser predominantly shining on the front keyhole wall, which helps because you get this wide opening, and you get a lot more stability because of that opening. So conversely, if we look at the previous case, we have this very narrow melt region, narrow keyhole, and then the laser is shining both on the front and the rear keyhole wall. So that's just a fundamental about this process that they could leverage to get rid of that porosity. So what they found was that just by increasing the speed and then correspondingly increasing the power so that they delivered the same level of energy, they were able to get rid of that porosity. So you can see here, 2.5 kilowatts, 3 meters per minute, you get a lot of that porosity. So they bumped up the power by 2 and bumped up the speed by 4. And then you can see they're delivering the same amount of penetration, but without the porosity. So that's kind of a simple solution here. Scanning faster isn't maybe always the answer. It does kind of change the process dynamics, what effect it has on thermal gradients and cooling rates, might impact your mechanical properties. So it's not necessarily the universal answer to all porosity, but in this case, it proved to be a very good solution. So there's a lot of technological advancement in laser manufacturing. And with this comes the ability to shape beams in different ways. And this, we know, has a direct effect on the keyhole shape. So the way that you deliver the energy is directly related to the keyhole shape. So these beam shaping technologies, they use a series of mirrors to kind of redistribute the irradiance, and they can create all kinds of different shapes. So they can do these kind of donut shapes down here in the bottom right, ring beams, multi-core beams, but you can also look at shapes that are not circular. You can look at kind of tailed shapes and things like this that we'll look at in just a moment. But generally speaking, we're looking to leverage this type of technology to improve the process stability, get a better weld profile, reduce spatter, reduce porosity. So researchers at Warwick University looked into using these beam shapes to mitigate porosity in another aluminum 1060 alloy, and they were working specifically in battery manufacturing. And so they actually used, they were exploring the use of tailed beam shapes. So it's pretty much an energy distribution followed by a lower distribution analogous to a tail. And so what you could see in these initial experiments here and simulations, this is their validation right here, was that they had significant porosity along the fusion line. And this is with the Gaussian beam. So you have these really narrow, deep keyholes that you can see were compared with simulation. Good agreement there. And in this case, they were using a 10 kilowatt coherent laser for the Gaussian experiments. So looking at reducing the porosity with the tailed shapes. So this is an example of the heat fluxes that they used in the simulation. So this is your Gaussian shape, your kind of classic bell curve, and then they used two beam shapes. So this one is an elliptical shape, and then you have this tail formation at the end, and this one is a rectangular shape, again with a tail formation, so a wider distribution. And looking at these through the simulation, you could see that you get that same kind of melt pool stability that we're looking for. So in the classic Gaussian case, you get these really deep, narrow keyholes. There's a lot of porosity formation. So we're trying to mitigate that. In the cases where with the tailed beam shapes, there is this wider opening of the keyhole. And then you get this recirculation zone is further away from where the laser is located. And so that's kind of the key here in terms of the stability. You want recirculation to be away from the front keyhole wall as much as possible. And so in looking at the effect this had on the porosity formation, just the fundamental kind of takeaway here was that the deep, narrow keyholes were leading to that porosity. And we can relate that back to what they're calling the K ratio, which is the depth to width ratio. So you want to reduce that ratio. You want to make sure that your depth isn't dramatically higher than your width. And then with the tailed shapes, we get a much smoother weld interface. So that fusion zone, they were able to get rid of that porosity. You get a little bit more variation on the surface here. So that is a bit of, a consideration here, but getting rid of that porosity was the main goal of using these shapes. So using this kind of software, being able to get those deep insights, they were able to reduce the number of collapse events that led to that porosity. And ultimately, this is going to improve the durability of the joint and reduce the electrical resistance, where that is the whole point of these connections in the battery. Now, looking into parameter development, which is really related back to defect mitigation, of course. So we're looking at process windows that avoid certain defects. There might be a lot of solutions here, so it's not just one answer, but you're going to kind of look for those zones that are acceptable process parameters. Maybe there's some that are perfect in terms of the joint integrity, but then you kind of want to balance that with production costs. And then there's going to be some parameters that are not acceptable, and those will happen kind of on the extremes of your parameter window. So how can we leverage a simulation to understand and to design those process windows? Ultimately, we're looking at joint integrity. That's kind of the end of the day, what is needed to kind of define those extents. And this comes back to the uniformity of the fusion, the morphology of your bead, the relative heat affected zones, and then the presence of defects. So we can kind of say, qualitatively from a high standpoint, these are the things that we're trying to achieve with a given process window. So the workflow that we take in a simulation standpoint, and you see this in almost all these studies, that you start off with a validation of known parameters. So you do need to have some information, at least on a starting point of where your experiments deliver, what kind of joint dimensions are you getting. So this is an example from Grundfos, where they, this is the initial to their study that they provided us, where you can see the validation is quite good. So we are capturing that bump formation. So that's your bead kind of morphology. And then you have the penetration, which is going to vary along the distance, and then compare that with the experiment. And not only this, but they were welding on this curved surface. And so they compared the simulation to the penetration in the experiment along the length of the bead. So you want to get good agreement just in general with your experiment in terms of the dimensionality. And then you can go into varying all kinds of stuff. You can vary process parameters. You can vary joint configuration. So Shiloh Industries provided us this example of their simulation. So they were looking at 2 different joint configurations. This is a butt joint where you have the bottom surface in alignment. So there's not full penetration of the weld into the bottom plate. So you get this surface morphology here on the joint and on the top. And then in another case, they ran, they actually had an offset of this joint. So they needed to do full penetration through both plates. And so you can see the agreement there between the top and the bottom surface profiles. Simulation is down here in red, and the experiment is the image on the top, of course. So the process parameters themselves is a big matrix, right? There's a lot of combinations of things that can impact the final solution. And then when you add in multiple materials, this becomes even more complicated. So we're looking at this process window and its sensitivities specifically to the various parameters, the various factors. And in this case, with dissimilar materials, you have different thermophysical material properties that will create this kind of spatially variant flow field based on the fact that the material properties, the fluid properties of the material are different. You have a case where they're naturally going to have different densities. So the more dense material will not sink to the bottom, lower density material will want to rise due to the buoyant forces. And then the material concentrations will have their own kind of mixture and effect on the flow properties. Certain concentrations are going to lead to brittleness, crack formation later on. So kind of controlling that interplay of the two material, you want to get good fusion, but you don't want to overmix the materials to the point where you're getting these kind of intermetallic compounds. So Warwick University looked into this as well with their battery manufacturing, and they wanted to see how that beam shaping could then affect the process stability when fusing dissimilar materials. So we can see here a lot of their experimental validations with the simulation. So this is a lap configuration of copper to a nickel plated steel. And they used a lumentum core light beam that had a beam shaping ability to it. So they had a inner core 55 micron and an outer ring 220 micron. And so you can see throughout these different comparisons here. So the experiment is on the right-hand side in each of these images. This is actually an EDS element mapping. So they're looking at the concentration of the materials. And then on the left-hand side, you can see in the simulation, we are also comparing the concentration. So there's not only good agreement in terms of the joint profile, but also of the concentrations of the various materials in the joint. And so they wanted to look at, again, the beam shaping. This is very interesting in terms of process stability. It really unlocks a lot of potential. Because of the natural challenges associated with welding dissimilar materials, and that you have these kind of contending fluid flow forces sometimes that are very dramatic, the keyhole stability becomes even more of a kind of process challenge to control. So in this case, they tested 4 different beam profiles. So if you look here on the bottom right, these are the beam profiles plotted in an XY kind of format. And this is actually how you would pull it into the software as well. It's just a direct import, and then we would represent the heat flux however you could possibly dream up to defining it. So they tested a couple of Gaussian beams. You can see they're overlaid, so it's a little bit hard to discern, but we have a kind of wider Gaussian beam, a narrow Gaussian beam, and then we have a Gaussian beam with this tail. This is in yellow, but you have this bit of a tail coming out here. And then we have a multi-core beam. So this is where you get kind of this outer ring, which is a lower energy density, and then a peak in the middle, and then an outer core. So they did model calibration with the Gaussian beams, and then they used the simulation to explore the beam shapes. So this is some of their results here, and we can see just by looking at these cross sections of the simulation that for the Gaussian beam, let's see if I can get that laser to come back. There we go. We have this deep narrow keyhole. This is just a higher power here on the right hand side with that LBS1 case. So of course, when you have higher power, you're going to get deeper penetration. You get a lot more fusion. And so in the case with just our kind of lower power Gaussian, you get a lot of fusion, but not so much penetration. Then with the next kind of peak, more narrow Gaussian beam with a higher power, you get a lot of mixing there, right? So you're getting fusion, you're getting a lot of mixing. And then when we look at the multi-core beam, we're getting more of that keyhole stability. So the keyhole itself is actually doing that kind of widening that we tend to like to see in terms of not getting porosity, but then you're kind of contending with a lot of mixing right here. The same with the tailed shape, we're getting more of a narrow, but still a lot of mixing. So how much mixing can you kind of handle, and how much does that result in, porosity, trying to reduce that mixing? This is where you need to kind of look at balancing the two outcomes. So just because you're getting better process stability doesn't necessarily mean that everything else is equal and that you're getting the right amount of energy delivery to, you know, fuse the materials properly or get the right thermal gradients for mechanical properties. So there's different kind of maybe sometimes contending goals that you need to consider. In this case, the stabilizing of the keyhole dynamics seem to be in direct contention with the mixing. So if we just look at that one more time, and we see with the higher energy delivery here, we're kind of spreading out the energy. So it's kind of just creating a larger melt pool, and then that larger melt pool is giving the material more time to mix. It's giving the lighter material more time to try to rise to the surface and things like this, which maybe isn't the optimal outcome for this case. So considerations for your weld schedule. You want to usually have a lower depth to width ratio. You want to have like a wider keyhole that typically will relate to better process stability, but then you want to look at, you know, how that wider keyhole is affecting other things, and how those might be kind of in contention, and then find your sweet spot. So that's your process window, and that's your weld schedule kind of that you have to work with. So it's not just, you know, the speed, the power, and the heat flux distribution, but you can also look at the effective scan strategy. So we saw in the beginning that wobbling case that was used to create process stability, but you can also employ all kinds of creative scanning strategies. So in this case, some of our users at General Motors were looking at a spiral scan strategy to improve process stability because they were having an issue with spatter from a zinc, trying to laser weld a zinc coated steel. So what they had, and this is a schematic, of course, that coating is very thin, but the zinc coating is in between the two plates, right? So this is a fang interface. And the issue with coatings and zinc coating and nickel coating and all of them, for the most part, is that they have a lower vaporization temperature. So you get these like vapor pockets that will form inside the molten steel. And of course, they want to rise. They want to get out of that molten steel due to their own energy and their own buoyant effects. And that will result in spatter. So what they did in this study, they didn't actually model that fang interface. We didn't have two material capabilities at that time, but they did still use the simulation to actually look at local pressure and temperature, and then use that to predict where the vaporization of the zinc would occur. So they were trying to reduce the local pressure within the melt pool so that they could control that kind of spatter. So you see good agreement here in terms of the experiment compared to the simulation. The experiment does have a bit of mass loss here at the top, and that's because of the spatter ejection, which they didn't capture in the simulation because they weren't actually modeling the zinc vaporization, but they were looking specifically at the local pressures so that they could control that zinc vaporization. And they ran these experiments with a 6 kilowatt IPG as well. So in this case, they actually did revise their weld schedule based on what they got from the simulation. So they used the simulation to understand where that zinc coating was going to vaporize due to the pressure that was predicted in the simulation. And then they proposed a weld schedule using different process iterations that they were able to simulate to lower the pressure in those certain areas. And what they found was that by reducing this initial line energy, so you can see the original weld schedule is here in the blue. So they kind of ramped up the line energy, and then in the proposed schedule, they made that constant to begin with, and then they were able to reduce the spatter. So then they go back to the experiment, and they were able to actually confirm that this new schedule did indeed produce a smoother weld bead. So this is a spot weld, it's just a spiral weld. So spiral welding is useful in all kinds of different applications, and we see this a lot in hairpin welding, where you're joining a bunch of copper windings for electric motors. And there's a lot of considerations in this process. So you want these to be lightweight, right? And that's kind of a huge part of EVs. You want them to be able to withstand a high temperature, a high thermal stress, and not distort. And you want them to be able to handle enough torque in this motor. So those are kind of challenges from a design perspective. From the processing side, there's difficulty in that this is where variation comes in. So you're welding hundreds of connections per part. So this is a very repetitive process. But naturally, in the real world, not everything is ideal. Not every winding is going to be exactly the same as the next, at least in terms of the process, the environment, the maybe kind of dust that is floating around. There's different things that can happen. And then also overheating in this case, it's copper, it's very sensitive to heating. It can get hot very quickly. So this is something that we know leads to porosity. You have those really deep keyholes that form. So looking into this, there's still a lot that can be done in terms of process optimization. And actually, Marcin, who's on the webinar today, did a simulation study based on this paper where they were studying experimentally the influence of power and spot sizes and wavelengths and beam shapes on the mechanical strength of these joints. So they were essentially breaking them. So this is the copper, this is schematic, of course, but they were breaking these in half, and then they were looking into them to see, what kind of porosity are we getting and what kind of joint integrity and joint profile are we getting. So Marcin ran simulations to see what we could see into this process about the porosity, about the joint profile, without doing all of this destructive testing. So of course, he started off with a validation. That is step one in any case. And so we get a lot of dynamics here. You can see there's a lot of kind of folding of the joint. You get this sort of top bulge on the top. And then if we overlay the experiment, it's quite phenomenal, actually. Let's look at the next screen. We get a very good agreement, not only in terms of the bead profile, but in terms of the actual shape of these beads, these kind of folds right here. So this is very surface tension driven kind of behavior, viscous forces. I mean, it's quite phenomenal what we are seeing in terms of the comparison. If it's not obvious, the simulation is on the left in these bottom cases. This is a ray tracing, and then the experiment is on the right. And then not only did we capture that bead profile quite well, but we also captured the porosity. So in this case specifically, there was a big pore that formed right here at the base of the joint, which we captured. And then we also see a lot of little speckles in here, and that's what we would call microporosity from this simulation standpoint. And we can track that as well. So we use these particles. These are subgrids. They're not actually resolved, but we use these particles to track the microporosity, which we see there's quite a lot of in these hairpins as well. And of course, these are meant to conduct electricity. They need to be as uniform and lacking of porosity as possible. So what we can see from this process is that, there's a deep keyhole that forms, and this is really why we're getting so much porosity, but there's no real avoiding of that keyhole. And because it's such a tight area that you're welding, there's only so much kind of widening of the keyhole that you can do. So looking at how this instability forms, what are those collapse events, and how are this process parameters going to affect that porosity is really the key to the simulation. You can only get so far with those experiments and the destructive testing. But the issue in this case was that pore, that large pore, the what we would call macro pore, is going to lower the mechanical strength. And this is a case that might actually, in fact, lead to a part failure, which is going to, come up for the consumer later on. So just to wrap it up, what simulation can do for you from what we've talked about today. We're trying to identify defect root causes. This is key to preventing defects from making it out to products there in the world. Evaluate how process parameters are going to affect your defects, affect your joint quality, and do this in a more systematic way, trying to avoid so much guess and check and iterations. That's going to naturally reduce the time associated with experimental trials, the amount of material used, the man hours used, the machine time used, and ultimately improve the weld quality, improve the productivity through having these deeper insights about process stability and how different parameters are influencing the joint integrity. So why Flow 3D Weld? We have a software, like I mentioned, that has integrated physics for modeling welding. So there's no user code development. There's no need to have a CFD background. This is all designed specifically for the R&D engineer, process engineer to understand and get a better feel for their welding process. We have dedicated technical training and support that's application specific. So we help our users every step of the way, setting up their simulations, changing their simulations, training them, training new users. So it's very hand-holding, we like to say, and yeah, we're there for our users for their entire modeling journey. And we've been producing reliable CFD solutions for over 40 years. So Flow Science is the developer of Flow 3D Weld, came out of Los Alamos National Labs in the 80s. We've been working with different manufacturing industries for lots of time, casting, additive manufacturing. So we really look at this from the perspective of the engineering problem. How can we solve that problem rather than just the kind of academic CFD perspective? Yes, thank you. I'll take questions, but I do encourage you to send me an email, connect with me on LinkedIn. More than happy to chat about any of this and discuss how simulations might be able to help you more specifically.
Okay, thanks very much, Elise. I'm going to hand over to Martin now to run the questions and answers.
Sure. So I have selected here a few questions for live answering. Let's see through how many we can go. So the first question from Akash is, will wider keyhole produced by tail extension help to penetrate the same depth compared to the keyhole formed by Gaussian distribution? But yeah, so to my understanding, the question is whether if we change the beam shape really by extending the portion of the heat flux at the tail will help to penetrate the same depth compared to the Gaussian. It really depends on the other parameters as well. that's so
process specific, yeah.
Yeah, that's the basic answer. Of course, assuming we keep the same power, if we extend the beam shape towards the end, it will likely produce a smaller penetration depth. Typically, the Gaussian beam gives us the highest irradiance peak at the middle, which actually is driving this recoil and evaporation and therefore the penetration. So it really depends, but I would say for the same power, probably Gaussian will give us a higher penetration depth, but not necessarily a similar stability of the process.
Nor width, right? So depth and width are both important. Exactly. I mean, that's kind of the whole point of simulation, is that none of this is that directly predictable. So having the ability to really understand the influence of the parameters that's kind of the whole point.
Yeah. So the second question from Akash is how to identify the heat affected zone through simulation with variation of welding parameters. And now, so what our users typically do is they actually identify the heat affected zone at the time of the post-processing. So they would look at the different temperature isolines essentially for their own materials. So there is some experimental input here needed, which is basically the knowledge about your material, right? Depending whether it's what kind of steel or it's aluminum, it will have a different isotherm temperatures at which it will be affected and differently affected. But you can easily extract this information from the simulation. You know at which location in the melt pool there is a certain temperature. So drawing an isoline of temperatures is very easy, and then you can draw the heat affected zone. Ali, I don't know if you have anything to add to this.
No, that was a good answer.
The third question here from Ataraf is, what is the most optimum penetration depth in the underlying layer relative to the thickness of the underlying layer? Optimum depth to ensure least material mixing, but ensuring mechanical strength. And here it really depends on the requirements for the weld, I would say. So the driving factor here is the what will be the mechanical stress to which the weld will be exposed, of course, right? That will decide upon how small the actual interface can be, meaning how much you can penetrate to the second layer. I assume this is, yeah, in kind of lap welding, for example. But really, the more penetration, the more mixing. So this is very well correlated kind of behavior. So the higher penetration requires a higher recoil pressure, higher evaporation, and that gives us the convection inside of the melt pool, which is actually causing this mixing. Sometimes there is also the buoyancy effect. So if we're, for example, welding the steel to aluminum and aluminum is the bottom and it's lighter, it's going to be pulled up because of the buoyancy. But generally, the higher the penetration, the higher the mixing, which of course, in many cases is a drawback. So the hope is here that, for example, with beam shaping, we can somehow break this correlation, but I haven't seen.
And this is a good example of where it's simulation is never going to just entirely replace your experiments. And there's a lot of kind of correlations that need to be drawn between what you know from your experiment back to the simulation, to use the simulation to find the optimal parameters. So there's a study, which I didn't talk about today, from GM that they found that there's a certain concentration of copper when doing a lap weld that would increase the propensity of cracks to form at the surface of the material. And so they were using the simulation to reduce the amount of mixing below that threshold that they found more or less experimentally. So it's a kind of back and forth relationship, but the idea is to use the simulation to better understand what it is during the process that's affecting something that you're seeing in the real world.
Yeah, I've actually done a similar study as well. And I even coupled it to our other software, which is called Flow3dX, which is like an optimization algorithm. And I was hoping to, find the parameters that give you the same penetration, but for example, a lower mixing of the, in this case, it was still steel to aluminum. And then what the optimizer did, it did its job. It was trying to vary parameters as much as possible, but actually what you get is just a straight line. I mean, the more penetration you get, the more mixing there is. So it was very difficult to find a sweet spot of parameters that would give you a high penetration, but no mixing at all.
Did you use a pulsed weld in that case?
Yes.
Did you try?
Yeah.
Okay. Because I think pulse welding is maybe one kind of idea to a solution to that. But yes, of course, it's a direct kind of course, the more you fuse, the more you mix. I mean, that's just kind of the nature of the situation.
Yes. Okay, let me take a look at other questions. So the next question from Daniela is, can you go backward and for certain process propose a beam shape? This is a very interesting question, actually, and I think you can. We haven't done this in a company personally, and I haven't seen a study, but I think this is on the way. So basically, for simple shapes, I think it's actually quite straightforward, maybe to at least implement this in Flow3D, because, for example, imagine a typical two fibers where you have the central peak and then you have the ring shape. You can vary well predefined parameters, such as, for example, the actual width of the ring, or how much power you have in the core, or how much power you have in the center beam. And by running an optimizer, you can vary those to get a certain effect or whatever you're trying to optimize, whether it's stability or penetration. So you can actually go backwards a little bit and trying to find the right beam for your process, beam shape. This becomes even more critical when you start looking at these dynamic beam shapes, which are now becoming popular. So basically you can draw any shape. You're not any longer limited to just, a Gaussian spot in the center and then the ring beam, but you can have a spiral, you can have a star, whatever you like. And this is more difficult, but I would say the simulation will really play a crucial role, because you cannot really simply do a DOE on this in the lab. You really need to have either, run many simulation and have the algorithm teach itself to where to go to find the right shape. So yeah, I think this is where simulations are going.
And to that point too, I mean, sometimes you're testing, like in some of these studies you're testing shapes that you don't have access to experimentally. And I know we have some users that use the simulation to explore beam shaping and laser powers and whatnot to make decisions about what to build into the machine. So kind of exploring the process before making a large investment into a laser to make sure that that laser is actually going to produce the kind of stability and process and outcome that you want. So there's, I mean, yeah, there's probably a lot of work, probably a bit of machine learning involved in kind of backtracking, but there's still a lot that you can do on the exploration side to kind of hone in. That is not just a brute force experimental approach.
The next question here is how long time does the simulation take in your examples? There was a similar question which I answered. I don't know how the examples that you showed, Ali.
So a lot of these, as you can see, is from our users. So I don't have that exact detail, but generally the simulation runtimes are going to be on the order of low end would be like a few hours to like a few days. I mean, it kind of varies. Or this is all done on desktop machines at the moment. We have we'll have MPI, which is HPC capabilities coming out later on this year, but all historic studies that you'll see in our bibliography, for instance, which there's hundreds of studies in there, are all done on desktop computers. So yeah, usually range is going to be anywhere from a few hours to a few days. This depends on your resolution. It depends on how big of a weld you're modeling. There's different factors that come into play.
The next question that I see here is the software able to simulate other processes such as gas metal arc welding? You want to answer that one?
Yeah, sure. So we have, at the moment, we have what we call a simplified model. So what is different about gas metal arc welding to laser, of course, is that you have a torch and it's delivering energy, not only the heat delivery, but there's a pressure field associated with it, just kind of from a functional, from a practical standpoint. So in the simulation, we are not explicitly solving the electromagnetic forces that give that pressure distribution, but we do have a solution to define a time-dependent pressure distribution that is in addition to any sort of shield gas effects or recoil forces or other pressures. And so for the moment, that is the solution, and it works quite well. The testing that I've done, if you have the information about that pressure distribution, how easy it is to get that experimentally, that's a question that I don't know.
The next question is, what is the material data set that is required to perform an accurate simulation, and how would you create a material set for a new material data set for a new material? And here the answer is typically there is a need for the most basic thermal fluid properties such as density, viscosity, specific heat, specific
thermal conductivity.
Capacity, thermal conductivity. For keyhole welding, important parameters are also the parameters of the metal vapor, such as specific heat of the vapor and the latent heat of vaporization of the solid to liquid transition. But we actually do have a database inside of the software that gives you all of these for the most basic materials, or for the set that we have in the software, which covers some of the basic ones. Then additionally, for the laser welding, the crucial parameter is absorptivity, which again, for the commonly used materials, we do know those values, but it's typically the one that is difficult to get, especially if one needs to account for the absorptivity as a function of temperature. Those data are really rarely accessible. So we have actually several users who develop their own new materials, which are typically based on some kind of a prevailing element there, right? Whether it's steel or it's aluminum alloy, and then this one element that takes the majority of the composition is probably your starting point for the material properties. But again, for these basic thermofluidic properties such as density, viscosity, and so on, we can actually generate those for you based on the composition. But the main challenge is on the absorptivity that can be changed by all of these small fractions of different elements, right, which are added to the alloy.
Well, I'll also mention on the absorptivity, it's not an intrinsic material property. It also depends on the wavelength of your material. It also depends on your surface roughness. There's other things that will affect the energy delivery. And in fact, the plume formation, the vaporization, so it actually changes during the process as well. So that definitely is a parameter that is a little more challenging to kind of converge onto, but there's actually a way to find that value via the simulation using the experimental correlation. So if you have experimental data, that's usually step one to, so to speak, tune the model, is that you want to match those bead cross sections, and the absorptivity is one of the things you need to look at in terms of kind of finding the right percentage of energy that is delivered.
The next question from Mohammed here is, I'm working on Flow 3D AM and wanted to know if there are any different assumptions needed for simulating the keyhole or Meltpool dynamics in AM comparing to welding.
I don't think so. I
Yeah,
mean, from our
wouldn't say
experience,
so.
I would say no. I mean, the scales are different, right? So in AM, you're looking on the order of maybe hundreds of microns, maybe less, couple hundred microns depth.
Because of the presence of the powder,
That changes things too. Yeah.
Perhaps
So there are some Mohammed, you should definitely reach out to our support and we're happy to help you with that type of a.
So
we have 2 minutes left, Martin. So I just want to make sure that in case there's
Yeah, I think there was 1 or 2 questions on Flow 3D AM, and maybe we can park those ones and answer them later, or
Sure, we'll write to you.
Questions here, so I don't know if we will be able to answer all of them at the moment. But
so what we'll do definitely is we'll we have the list of all the questions, so we'll write to you as a group and make sure that we get answers to all of them. We have other materials for Flow 3D AM specifically. There are different considerations when you're dealing outside of when that's a different process, but the physics are fundamentally similar. So
there's 1 question here from Neil Main speaking about tiny welds, say 50 microns to 0.5 millimeter. Does it work with really small welds? And also, will it find the temperature, say 2 millimeters from the weld for electronic systems? So if you have some very heat sensitive materials that you're using in your packaging, for example, can you read out the temperature 2 millimeters away?
Yeah, so tiny welds is analogous to the AM length scales. So yes, we can look at kind of micro welds, so to speak. And then in terms of the heat affected zone, we do predict the conductive heat transfer through any sort of kind of solid adjacent material. So if you account for that in your domain, then yes, you can see kind of the thermal profile amongst the entirety of the domain. So say you have like a little plastic piece, or you have something that you're trying to, reduce the temperature on, you can also set like a probe in that location. And then using this optimization algorithm, you can use that as like a target goal, find process parameters that keep the temperature at this location below a certain point.
Yeah, and even if you have very small melt pool, but you're actually looking for a temperature which is further away, like in this case, 2 millimeter away, you can set up several mesh blocks with different resolutions. So the further you are from the melt pool, you can have a larger cell size and still reach that far distance and temperature field.
Okay, so we'll follow up with the rest via email, Dave, unless you've
there's maybe 1 more question.
Okay.
Mitchell Leering's asked if it's possible to apply multiple laser beams, e.g. multi-wavelength or pulsed and CW simultaneously during the simulation.
Yes, so you can independently define up to 100 different beams. Not that you would do that probably, but yes, they can all be independently defined, their distribution, their delivery. You can do pulsed, continuous in the same simulation. They can have different scan paths, completely independently defined. Yes.
Okay, thank you very much. I think that probably brings us to the end of our time slot for the webinar. Thank you very much to Elise and Marcin for presenting and answering the questions. As Elise mentioned, any questions that haven't been answered and can be answered physically will be answered after the webinar, and an email of all the questions and all the answers that are given will go to everyone who's registered for for the webinar. And just to remind you that the video of the webinar will be available. Give us up to a week to get that online, and you will get a follow-up email with access to a link to that video and also a PowerPoint slideshow with the animations that Elise has presented today.
Awesome.
Okay.
Thank you, Dave.
Sounds good.
Thanks for
Thank you
hosting
very
us.
much, everyone, and I'll say goodbye.
Okay, bye. Have a
Bye.
good day.
Thank you for watching. Bye.